All right, hi everybody. My name is Jesse Wilson, and I'm gonna somehow manage to talk to all of y'all about JSON for an entire full-length talk. Wish me luck. JSON stands for JavaScript Object Notation. It always really existed in JSON, in JavaScript, but it was identified, named, and popularized by a guy named Douglas Crockford, who's a really big, important person in the JavaScript community. He took that format, he formalized it, documented it, and built a bunch of different libraries so that we could use JSON in our Android apps, server apps, Ruby, Python, everything. So he really put all the initial momentum into JSON, and we're all the ones benefiting from it years later. That project started around 2002, and the initial implementation, the initial JSON projects were under a website he created called JSON.org. And so if you have seen in the Android code base, there's a package called org.json. That's Doug Crockford's package and his API. And if you look at the original license to that code, it's your standard, internet nerd license, except for this one little detail. This software shall be used for good and not evil. And this is where my story begins with JSON. So I was working at the Google Corporation at the time, and somebody said, hey, this software should be good and not evil. That actually isn't an open source license. People who use open source software should be free to commit evil with their software. It's part of the open source definition. There's a thing called a no discrimination against fields of endeavor. And we want to allow both Iron Man and Hulk, but also Thanos and Theranos to use JSON. So I got involved. They said, Jesse, we're going to have to re-implement the JSON implementation so that we can build it under an actual open source license. And so I rewrote org.json in the Apache re-implementation of that API. So my original work was 2008, taking org.json's completely reasonable JSON implementation and writing a version that could be used explicitly for evil. And so I'm going to go really briefly into what JSON is, because it's so simple, we already know it, right? There's an RFC, there's actually been a few, 4 sort of basic types, 2 container types, and I'm just going to rip through all of these. It's going to be super fast. Booleans, these are delightfully boring. I feel like as a software engineer, I love describing things that I think are awesome as boring. It's like, oh, running MySQL is a great database because it's boring to operate. You don't have to be constantly babysitting it like these other databases. When I describe things as boring to like my friends and coworkers who aren't programmers, they're like, did you just diss that? I thought you really liked it. I'm like, no, it's boring, it's best. On iOS, Boolean is an NS number, and because C existed a long time ago, they get 0 instead of false and 1 instead of true unless they configured things up. But on Android, we never had this problem. Numbers, how difficult could this be? It's just a standard IEEE 754 double precision floating point number. Not at all boring. But let's just dive into some details. I'm going to give you a refresher on floating point math. So we got floating point numbers, float and double, 32 and 64 bits, specified by a different spec. They're supported by Kotlin, Java, almost all programming languages. The floating point numbers that you use in JSON and that you use in Kotlin have support all the way down to your CPU cores, not just on your CPUs, but also on your GPUs. This IEE floating point is inescapable, unavoidable. It's a dominant industry standard. And so maybe we'll talk about how numbers work. We all remember being in grade 1, grade 2, grade 3, learning about the natural numbers, 1, 2, 3. Super easy, this number set, love it, easy. But ultimately, if you want to do anything interesting, you need integers because you need to be able to do subtraction, you need to be able to represent 0. So the integers is a set called Z, and we draw it with that cool double line. In grades 4, you get into these like division. Division sucks. You get rational numbers like minus 22 over 7 or 51 over 100. And a rational number is a number that you can express via a division of integers. And then the real numbers is a number that you can, is that plus any number that you can express sort of like functionally or procedurally, like pi or the square root of 2. And so we have this like rich number line that we learned about in elementary school. And what's really important about this number line is that the elementary school number line, no matter how far you zoom in on the number line, you can always point to a space and there's a number there. Computer numbers, they take a lot of liberties on computers. So a byte is like an integer, but the range is really, really short. In Java and Kotlin, a byte begins at minus 128, goes all the way up to 127. The fact that those boundaries aren't the same number is like occasionally annoying. If you say minus 128 and you multiply it by minus 1, you get minus 128. That sucks, but other than that, byte type's pretty reasonable. Short, same thing but bigger. Int, same thing but bigger. Long, I think that's minus 9 quintillion all the way up to 9 quintillion. So that's a useful number if you have to add up a lot of things. But we're here to talk about floating point numbers. Floats are a subset of the rational numbers of Q, which means that they're not capable of representing values like pi and e exactly. And so a float, 3 plus, I think that's 7 decimal digits of precision. And the reason that there's 7 decimal digits of precision there, even though the pi that we know in our hearts has many, many more digits, is because that is like the most fine granularity you can get to with a float. Double is way better. We get, that's like 15 digits of precision. So the floating point numbers, pretty basic. There's also 4 special values. They're called infinity and negative infinity, and you can produce these annoying values with the original values you were given. So 1 divided by 0 with negative 1 divided by 0. There's these like super annoying values in floating points called negative 0. And negative 0 is, it's a thing. And then there's this extra value called nan, and it's the floating point number system that's ubiquitous in our hardware brought its own alternative to null with it, and it's inescapable. And it's not null, but it's kind of shitty anyway. So each of these types is weird. Infinity is weird. If you take the string infinity, it has to have a capital I, exactly like I spelled it here, and you call double.parse double in Java or just two-double in Kotlin, that works. It doesn't give you a that's not a number exception or something. It actually works. And so if you are taking user input and your user says like, how many tacos do you want to buy? They can type in infinity, and if you're using double.parse double, you better have a lot of tacos. There's also negative infinity, same thing. Negative 0, also weird. It gets weird in weirder ways even. So the operators don't differentiate between negative 0 and 0. So for the most part, if you do some math and you end up with negative 0 in a double, and you check, is that equals to 0, and it will return true. But the methods do. So if you have, like, in Java, a boxed 0, or if you call the .equals function on it, that returns a different result than the equals operator. This offends me to my soul. Nan is weird, and it's actually weird in the exact opposite way that negative 0 is weird. So with negative 0 and 0, those two numbers were equals each other. Nan doesn't even equals itself, right? It's not reflexive. That is a really, really bad property for any value to have. The methods for nan are reflexive. So anything you're doing with floats and nans and zeros and negative zeros is just going to always be unpleasant. And if you look at any of like the core JDK code, there's a lot of extra special nonsense, right, just to deal with this stuff. So if you want to like sort an array of doubles, the implementation of sort actually counts how many negative zeros there are and how many positive zeros there are, or unsigned zeros. And it does that so that after the sort is complete, it can make sure that it hasn't accidentally flipped the sign of a 0. Yeah. All right. Nan has the same problem where you can type it as a string and put it in the put it in your text field and order Nan number of tacos. But what we want to actually talk about is the real like floating point numbers. And so it's a subset of Q. Q is, again, I said, numbers that you can create with a division of integers. So the reason it's a subset is it's every floating point value can be expressed as an integer division by a power of 2. So for example, if you wanted to express minus 127.5, that's just minus 255 divided by 2. If you wanted to express 8.875, that is 71 over 8. This one is a little bit weirder. If you want to express 0.1, does anybody know what power of 2 you divide by, what value you divide by power of 2 to get 0.1? Dramatic pause. Obviously, it's 3 quintillion. 3 quintillion divided by 3 quintillion. I think I have a decimal place missing, a comma in the wrong place in one of these. The most important part of this number, though, is if you look at the very end of this number. No, I'm right. It's 3 quintillion divided by 36 quintillion. But if you look at the very end of this number, the last 3 digits are 397 on one of them, and the other one it's 968. And so you'll notice that floating point numbers, in particular doubles, do not have an exact representation of 0.1. This turns out to be annoying. The way to think about where the doubles are on a number line is that as you get closer to 0, there's a higher density of floating point numbers. So there's a whole bunch of floating point numbers between -1 and 0, or between -1 and 1. And then as you get further away from 0, the values that you can express get further and further apart. There's 1 bit of the 64 bits you get for your float is for the sign. 11 bits is for the exponent of the denominator. That's which power of 2 to use. And 53 bits are for the numerator. So that 53-bit integer numerator. So let's talk about the distances between those values. In my number line, I showed like 8 values between 0 and 1. But in practice, between 1 and 2, for example, there is 4 quintillion values between 1 and 2. So you can get pretty precise. Between 2 and 4, the range is twice as big between 2 and 4, and the number of values is half as big. So there are 2 quintillion values between 2 and 4. Between 4 and 8, the range again doubles in size, and the number of values halves in size. And so you can see, this is distance between, so the ranges are continuously getting smaller as you get higher and higher up. Something interesting and offensive happens as you apply this doubling game over and over again enough. When you get to 2.2 quintillion, between that and 4.5 quintillion, there's basically every integer and that integer 0.5 available. So you can say, 2 quintillion something something 248, 2 quintillion something something 248.5, 2 quintillion something 249. Between 4 and 9 quintillion, there's a value for every integer. And between 9 quintillion and 18 quintillion, there's only a value representable by a double for every 2 integers. And this turns out to get really, really annoying. So mind the gap. Let's assign a value called x to 9 quintillion. And we're just going to take x. We're going to add 0 and subtract x. We get back 0. This feels like the math that we were taught in school. We're going to do the same thing. We're going to subtract 2 and we're going to add 2. Take x, subtract 2, subtract 2, subtract x again. You get back -2. X plus 2 minus x, you get back 2. Nothing earth-shattering. This feels safe. Let's put 1s in here. So x minus 1 minus x is -1. X plus 1 minus x is 0. This turns out to be really, really annoying. And when you're working in floating point numbers, at some point, there just aren't them, and there are gaps between values. And this is just like where you get to the edge of the universe and things just stop behaving the way you'd expect to be. So basically, all this math that you do at the very high end of the number line just stops working in the ways you'd expect. But it's not just at the high end of the number line that there are problems. There's also problems at the very low end of the number line. So for example, 0.1 plus 0.2, everybody knows that's 0.3000004. We learned that in school, right? One of the things that like sort of offends me and scares me and makes me like worried about computer programming as a craft is that these errors accumulate. So although 15 digits of precision is often far more than enough, you know, in order to do most of the operations that we need to do in our day-to-day life, you know, if we need to show a button at exactly the right place on screen, 15 digits of precision is usually enough. But if we're sending people to Mars and we do enough floating point math on the values, eventually that error compounds to be enough to kill astronauts. So we have to be really careful. Other thing is that although these values are fundamentally binary, you know, they fundamentally are about powers of 2, we basically always think of them in decimal terms. And there's all sorts of other weird problems where you go between a very precise binary value and a decimal approximation. And so there was this awesome, incredibly terrifying bug where if you pass that exact string to double.parseDouble, it would cause the algorithm that converts a double to a binary to hang. It would just send it into an infinite loop. And so this was a big deal in 2011. The day that this sort of like happened on Slashdot, I typed this value into a Google spreadsheet and hung a server at Google. This was discovered and fixed extremely quickly. I've never seen a bug fixed as fast as this one because you have this like basic simple string that can basically hang any server. So doubles are trouble. They're really important to remember that they're not like the numbers that we learn in math class. We've got -0, infinity, nan, and we've got these gaps. So decimal representation is approximate. This is the number system that we have to work with when we're working in JSON. So back to the boring bits. You know, how hard can JSON possibly be, right? The JSON spec says expect no more precision or range than double precision. So your JSON values go from about -2 to the 53 plus 1 to net 2 to the power 53 minus 1 is the safe range for integers. So if you're doing any integer-y things in JSON and those values are really high, be careful. One other thing that's weird is that JSON doesn't have infinities or nans, but it does have -0. And so if you're parsing a JSON document or you're formatting a JSON document and sending it to somebody, and you're taking input from your database or your application, and your application has infinities or nans in it somehow, it will crash on writing. And so it's just another form of like mysterious null pointer exception that Kotlin won't even save you from. One of the things I really want to emphasize though is that 2 to the 53 is smaller than a long, but it's a very, very large number, and so this shouldn't terrify you too much. So for example, if we have 2 to the 53 bytes, that's about 9 petabytes. So if you want to know exactly how long a download is going to take, if it's under 9 petabytes, you can compute that exactly. 2 to 53 milliseconds is about 285,000 years. So if you want to send like an epoch timestamp from like system current time millis, it's going to be a long time till you start being off by a millisecond. And 2 to 53 meters is enough to get you far out of our solar system, but not very useful to get to the next star. So if per meter precision matters to you in your space travel, you're doing something weird. So when we're working with JSON, it's really easy to say, here's my business model, the types in my business model, and the types from the mobile app to the server or whatever. You know, JSON happens to be the representation that we send the values in. You actually have to be careful of the fact that if you have a value on the server, you send it through JSON to the client or vice versa. JSON's numeric limitations come into play. the APIs you're writing will attempt, so all the JSON APIs you use will attempt to retain types and precision, but it won't round trip through systems that lack types. So for example, if you send a JSON document through a browser, the browser type will convert all of your longs with all their precision into doubles. Relying on anything more than 2 to 53 digits of integer precision is trouble. And really, really importantly, do not use numbers for IDs. If you just need a unique ID, calling like random.nextLong and then using that as an ID is going to cause you problems because that ID will get rounded or moved when it goes through a JSON conversion. Cool. All right, strings. Strings in JSON are UTF-8 encoded, quote delimited, and there's a bunch of escape sequences. Delightful. Null. It should be boring, and for the most part, null is pretty boring in JSON, but there's this one thing that I find annoying about nulls in JSON. Here I've got a JSON document. I've got 3 planets, Jupiter, Earth, and Mars, and Jupiter was discovered by Galileo, and that field is both present and non-null. Earth was discovered by null. We don't have a person who discovered it. And Mars, we just didn't provide that field. And so when you're thinking about expressing things in JSON, sometimes you say null and absent are the same, and sometimes you think null and absent are different. And it just helps to be deliberate or explicit about this. Arrays, so we're into the container types. Square brackets and closed comma separated values. Arrays are also relatively boring. Here we have those same planets, but now we've got inhabited by as an array. And we could have inhabited by with values in it. We could have it inhabited by null. We could have that array omitted, or we could have it empty. And so now we have empty, null, and absent as 3 different cases, and things where we want to be really deliberate about how we model arrays. Objects. Curly braces and closed, comma separated, name value pairs. So let's create a JSON object with some of my favorite planets and the first letter of their names. So J is for Jupiter, V is for Venus. There's a function inside of Java's hash map and linked hash map classes called hash bucket. And I bring this up because when you have a value in a JSON, we often take that value and map it to a map in Java. So the keys for the hash map, the keys and the names in the JSON object will become the keys in the map. And hash bucket is something from computer science class where we actually see how the hash table data structure works. And so the way that it pretty much works is we take the hash code of the key and then we mod it by the number of buckets. So I'm going to do a full computer science walkthrough of taking that set of planets and putting them in my hash table. I've got a hash table with 8 buckets, and I'm going to say, what's the hash bucket of my first planet, Jupiter? It's 2, and I'm just going to take that and put it in that bucket. So this is your hash table data structure. On to the next planet. What's the hash bucket? Venus, it's 6. We're going to go to bucket 6. There's nothing already there, so we're just going to put that Venus element right there in that hash table. Next one. What's the hash bucket of Neptune? Oh, it's also 6. And so what the hash table needs to do is it needs to actually walk through and see, do we already have a key, do we already have a value for the key n? And if so, we want to replace it. Otherwise, we just want to have 2 different values in this hash bucket. And so the hash table algorithm will look and do a linear search through everything in bucket 6. It'll say Venus, V is not n, and it'll add Neptune to the end. Last one, S, hash bucket 3. We put Saturn in there, and we have created our hash table. And so every time you're writing any interesting code that's taking in JSON objects and putting them in maps, it's doing this lots. This is basically how JSON keeps itself busy. Let's go to the exact same problem, but I've got a slightly different data set. In this case, I've got a bunch of strings, some of my favorite strings like ABCD and ACDC, and some numbers. Let's just use 0 for the values here exclusively. And so I'm going to take this set, and I'm going to put it in my hash table again. So what's the hash bucket of ABCD? Well, it's 7, and so we just put that right in there. What about ABD capital E, also 7. So we're going to say, let's see if that thing already exists in this linear list of things. Look at the first one. It's not ABCD. We'll put it at the end. Onward. Oh, I think you guys may already figure what I'm doing. ACDC has a hash bucket of 7. Put that there. ACEE has hash bucket 7. And so we got this value, and we're actually going to do, again, a linear scan. We're going to say, is it ABCD? Is it ACE? Is it ACDC? And then finally, we put it in its spot. And so every single time we look at one of these values, it's going to do a linear scan through everything we've seen before. And in computer science school, we call this a quadratic function, or an order n squared function, because in order to do n units of work, we have to do n times n scans. So we're going to keep putting these things in here. I'm running out of space. We're looping over ourselves. Our hash table is really turning into a linked list. A linked list is a shitty, shitty data structure for solving this problem. And so this is called a hash denial of service attack. And it works by providing something that is taking the data you give it and putting it in a hash table, and specially crafting the data so that every single value has the exact same hash code. These strings have not only the same hash bucket, they all land in 7, but they also have the exact same string hash code. You think of like hashing in like a cryptographic sense as like it's very difficult to create collisions. In Java strings, the hash codes are trivially easy to create lots of values that have the exact same hash code. And so I took this hash code of the ABCD string, and I took a megabyte of values of JSON that all have the same hash code, and I put it into an implementation of hash map that doesn't defend against this. And it kept my CPU core on my MacBook Pro busy for a minute. And then, obviously, quadratic, right? So let's do a 2 megabyte JSON document, keeps my CPU core busy for 4 minutes. And so if you're thinking about how to spend more money on AWS, you could potentially just send megabytes and megabytes to a server that's not responding to this. This attack was pretty popular when it was sort of first popularized, and it was fixed in the Gson library in 2012. It was fixed in OpenJDK 8 in 2013. If you put these things into an OpenJDK 8 hash table, once that linked list gets long enough, it actually takes the linked list and turns it into a balanced binary tree. It was fixed in Android Oreo 2017. This is getting into very recent history. And other platforms that I will not name here are still vulnerable to this attack. So something to be thoughtful of. One other thing to be careful about with JSON is that occasionally names can be repeated completely, not just the same hash code, but exactly the same name. So for example, imagine we're doing a JSON web token, which is a thing where you specify an algorithm and a type of the algorithm. So here we have a JSON document. The algorithm is HS256, and the algorithm is also none, depending on whether you think the first value should win or if the last value should win. This is very problematic if you're doing security systems where you say, okay, how are we going to validate the user's credential? Oh, we're going to use no algorithm? Cool, everything is good. And then you say, how was this thing validated? Oh, it was validated with a very strong hash function? Cool, I'm very happy. So it's very problematic that in JSON, it's very easy to repeat values, and most libraries in most situations will just take the last or take the first. And if you're building systems that are hardened and defending against data that's in JSON, the system that's doing the security enforcement should also be the system that's making decisions about how to disambiguate documents like this. Dates. JSON doesn't have a date format. RFC 3339, which is also basically a nicer subset of ISO 8601, is a good choice. And this is the one where you just basically specify everything, year, month, day, hour, minute, second, with a time zone offset. If you're doing any times in JSON, this is the only format you should use. What about binary? Sometimes we want to send, images or recordings or values or measurements in JSON. A64 is good if you want to put the binary data inline. URLs are also really good. So if you have a JSON document Sometimes you want to say, here's a value, it's a binary value, I'm just going to base64 encode it. Or maybe you just want to say, this value, I'm not going to include it here. Here's a URL where the application reading the JSON can go off and fetch it. So I want to talk about some JSON libraries and basically compare and contrast them so that you can feel bad. All right. So we've got Gson. Gson has every feature you'd ever want. It's fast. It's a Java library, but there's Kotlin support via a support module. Gson, tons of features, also fast. It's a Java library, and there really isn't like any thought to making Kotlin work in Gson, so it doesn't really work. There's a library that I work on called Moshi, and Moshi is, I like to think of it as taking my favorite ideas from Gson and modernizing them and bringing them into the future. It's small, fast. It's a Java library, and there's Kotlin support via a support module, just like Gson. And there's this new library that's new hotness called Kotlin X serialization or Kotlin serialization. It's small. There's no streaming support, so I sort of ding it on the speed. But it's got Kotlin multi-platform. The biggest drawback of Kotlin serialization is if you have a mix of Java and Kotlin classes, you're pretty much on your own for all the Java stuff. When we're reading JSON, we're reading it generally via streams. And so you'll get some data as a byte array. Here's another planet joke. We're going to start streaming before the entire JSON is downloaded. So we may be downloading 100 kilobytes of JSON, but we actually want to parse it as soon as we get the very first byte. Streaming parsers will typically either read the bytes as UTF-8 or they'll convert it to Java chars. When we're decoding an object, the decode loop generally looks like something like this. So we get a JSON reader, which knows how to take that stream of bytes and convert it into JSON symbols. Very first thing we're going to do is just define the fields that we need to pull out of the JSON and then return them as the result. We're going to call JSON reader to begin object to consume that very first curly brace, and end object to consume the end curly brace. And then reader.hasNext is this mechanism to basically read every name value pair in our JSON document. And then finally, working our way outside all the way in, for every key value pair in the JSON, we're going to read a name and then decide what to do with that name. So we'll read a name, and then if it's the string color, we'll take a string from the JSON and assign that to our color field. If it's the radius km name, we'll parse it as a long. So that's typically how JSON streaming decoders work. And then the biggest challenge with JSON performance is that if you look at this work, it's just allocating tons and tons and tons of strings. So the fancy JSON libraries each have their own interesting mitigations to avoid string allocation. A lot of performance optimizations are about effectively work avoidance. And so if JSON, the most expensive thing you're doing is string allocation, we want to find ways to avoid that. The naive thing, when you'll find some begin and end offset and then create a string. And so this is sort of the least performant path. I'll show you two different strategies for avoiding string allocation. In Gson, there's this fancy class internally that you never have to deal with, thankfully, called byte quads canonicalizer. And it has a really big integer array. And it takes every key in your JSON and it cuts it up into basically 4-byte chunks. Each chunk is represented as an int in this int array. So when we see the string color, that's 1 byte for the first 4 characters and 1 byte for that R. And that maps to the string color. And what's interesting here is that the second time it reads the string color, it actually reuses the allocation that it did the very first time. The string radius km, it uses 3 integers to represent that string, and then again it gets allocated once, and then it's kept forever. And one of the things that's neat about Gson is that the very first time you parse any object, this map gets created, and then it gets, or this hash gets created, and then it gets reused for every single parse going forward. There's mitigations for strings that are longer than, I guess, 12 characters. And then if you want to see how that works, I recommend you get yourself some popcorn and study that code.
Moshi takes a completely different approach for string allocation avoidance. It's called the options try. And what it does is, before you start a parse, you give it a set of input strings that are potentially the fields of your object. So here we're going to do, I think this is for a song object, and it's got these 7 fields. And what Moshi will do is it will take all the fields that you know you're going to ask for, and it's going to build a try out of these fields. And so if you see here, I don't know if you've done tries in computer science school, but basically we just take the very first character of every word and create a tree, not a binary tree, but an n-array tree, and then for every of those letters, we delegate to another tree node that either has a literal value or a fragment of a word, or a choice to make. And so when you parse with Moshi, it will take all the strings you're going to ever need to ask for, and it builds this custom data structure. And then when you want to use it, what happens is we go back to our original stream parse, but the very beginning of our stream parse, we actually tell Moshi, hey, these are the strings I care about, color and radius km. And then when you're inside your reading through every name loop, instead of saying, give me the name as a string, we say, here are a list of names I care about. Give me an index for it. And so if it's the very first one, we get back 0. If it's the, if we get index 0, we get 0. If index 1, we get 1. And then Moshi takes the corresponding next action. If it's a value it hasn't expected, it just skips it. And so it's a different approach to string allocation avoidance. All right, you'll read these JSON libraries and they talk about streaming and they talk about trees. And a lot of these JSON libraries have different tree models. There's Jackson's got its JSON node, null node, missing node, Pojo node. There's a whole bunch that I've actually omitted here. Gson has its. Moshi actually doesn't have its own custom node types. There's no JSON array or JSON object in Moshi. It just uses the built-in Java types. And one of the things I think is really interesting here is that Moshi doesn't have a custom type to represent a JSON null. So Jackson, Gson, and Kotlin serialization all have their own abstraction, which is a value that represents null. And Moshi just uses the built-in null from the existing type system. And every time I work with these JSON tree models, it just makes me really frustrated and sad because there's lots of strings, there's lots of casting, there's 2 kinds of nulls. So I've got like the boxed null, and then I've got also just the regular Java null that I have to normally deal with. And so I just really dislike working in these tree models. I find that it's really cumbersome, and there's some places where I want to like work abstractly on an unknown JSON where I don't know the schema. But in that case, I really, I guess I'm proud of Moshi's model, where it's not bringing a new set of types, it's just using what I'm already familiar with. But instead of trees, data binding is sort of like the where JSON actually really shines. So we take all of the built-in JSON types I mentioned at the beginning of the talk, and we just map them to types from our sort of Java or Kotlin type system. And then we build adapters that basically say, if there's a type in JSON represented as an object or a string, I want you to map that to a corresponding application layer type. So they'll convert between Kotlin and JSON. An example is like you may have a HTTP URL from OKHTTP, which you want to represent as a string in the JSON, but actually as a concrete type in your application model. There's a bunch of different problems we run into with binding models. So for example, if we have a graph and we say planets have moons, and then moons know their planets, what ends up happening is we try to serialize this, and it's recursive, and so the moon of Titan references Saturn, which again references Titan, and then it blows up and we get a Stack Overflow. Fix for this is just when you're building JSON, you have to reference things symbolically by their identity or by their ID rather than by their value. So that cleans that up. When we want to do polymorphism or subtyping in JSON, if we emit our cosmic object of star, planet, moon, this works. But then when we try to parse it out, we don't know what type Saturn is. We try and read name Saturn, and we don't know if we're supposed to instantiate a planet or a star or a moon. So the solution for this is something where each of these libraries has some sort of polymorphism support. Moshi's is called Polymorphic JSON Adapter Factory, and you basically just register every subtype that you care about, and then when you encode it or decode it, there's an additional name field, and the name field just tells it this is the type to look up. One of the things I find most that makes me most anxious about mapping in JSON is that there's a lot of magic that has to happen to make the data binding work. Gson uses reflection, Moshi uses reflection. These libraries all basically create your instances for you. And so on the left-hand side, we see that the color field is unknown by default. And if you specify it, it gets a value, but otherwise it's unknown. If we try and parse this JSON that doesn't specify a color field, I would expect the unknown value to emit, but if you look in the bottom right corner of the slide, it says planet color is null, and planet moons is null and not empty list. And this is really surprising, really frustrating, and it basically leaks an implementation detail of the way JSON libraries work. The solution, I think, the easiest solution is actually just to avoid Java from modeling JSON objects and use something that works with Kotlin. The Kotlin models basically have stronger understandings of the corresponding types. And so if we do that and we just convert this from Java to JSON, sorry, from Java to Kotlin, the JSON will do the right thing. And this is just because in the case of Moshi, it can actually see the names of the fields in the constructor. It knows that its name and radius km, and that's enough information for it to invoke the constructor rather than to basically create the instance by magic. There's another problem, which is that if you ever try to serialize a built-in type, like java.awt.color in this example, you end up potentially leaking the implementation details of the JDK platform you're building on. So, I say surface color is yellow, but when I print it, I get value is -9677 and falfa is 0. And I don't know what those things are, but it's because the JSON library is just sort of doing what I tell it to do, but not what I want. One other challenge with binding is that in JSON, our field naming conventions are often different than what is conventional in Java. So with Gson, there's a thing called a field naming policy, and it will take your camel case names and map them to have underscores. And I find this very troubling because I'm worried about what happens when we're relying on this. Imagine you're on your team and somebody comes to you from your server team and says, I'm deleting some old code. Does the app still use the orbits star field? And you're like, I don't know. Why don't I grep the code base? You search in grep or you search in Android Studio, and no hits for orbit star come up. This is a this is a problem because if depending on how you named your field, it may actually be there. And so the problem is ultimately the data that you're printing in your JSON and the data that you're printing in your application code. Ideally, those are always exactly the same. So if you search for one and don't find the other, that's a problem. One solution for this is just use the @serialized name annotation instead of using the field naming magic. This works relatively well. My advice for Moshi has always been actually just break with convention. The cost of retaining the convention is really the cost is really low and the benefit is really high. The other thing I really like about this is it's like a very bright signal to readers of the code that this value ends up in JSON. The binding libraries, both Moshi and Kotlin serialization, implement their binding via code generation, and that's interesting in that it just avoids reflection and it makes the code a lot faster. And so here it is, the moment we've all been waiting for, the JSON libraries, the JSON awards. And so we've got a bunch of different libraries I've chosen here. They're all relatively They're all relatively recently released, but Kotlin serialization is just very brand new and has a lot of rapid iteration. So Jackson, Gson, and Moshi have a stable API. They've all been around for a long time, and Kotlin serialization is the new kid, and it's unstable and it's changing very, very rapidly. The size of these libraries, Jackson has a dependency on the Kotlin reflect library, which means that Jackson itself, with that library, is 4.3 megabytes in your APK. Gson is 239 kilobytes. Moshi is 330 kilobytes, but that includes the OKIO library. And then Kotlin serialization is about 760 kilobytes with its dependencies. Because Moshi and Kotlin serialization both generate code, that will also add to the size of your binary. They all have different performance features. I'm not actually going to give you a benchmark and say this is the fastest JSON library, because all of these benchmarks are ultimately really dependent on the VM that they're running on, if it's Android or if it's the desktop JVM, if it's Art or Dalvik, and they're also really dependent on what the structure of your JSON is. So if you're using Jackson and that byte array byte quads class ends up being really effective, then you'll have really good performance, but there will be different types of documents that will benefit or not benefit from those optimizations. Jackson's performance features are fast encoder and that allocation avoidance pool. Moshi's got a select try, and Kotlin serialization has generated adapters. Note that Kotlin serialization doesn't have a stream encoder, so you have to download the entire document before you can begin converting it to JSON. We've got a bunch of different APIs. They all look relatively the same. They basically take a type and they give you they take a type and a string or a stream and give you back a value. So there's Jackson and Gson and Moshi and Kotlin serialization. They all look relatively the same. They all look relatively the same if you want to install a custom adapter. So this is what code it looks like to make an adapter for the HTTP URL class with Jackson and Gson and Moshi and Kotlin serialization. And those functions all look basically the same. You write some function to go from JSON to your value and from your value to JSON. They all have different usability strengths and weaknesses. With Gson, one of the things I think is weird is that if you have an ampersand in your code, it gets encoded in the JSON. This is a artifact from a design decision Gson made a long time ago, and it's still there. And one of the consequences of it is just when you're reading your code, the U0026 may not jump out as you as ampersand. When you're using these libraries and you're in development or debugging problems, sometimes you'll have a situation where your application code doesn't directly match what's in the JSON document, and they give you different levels of errors here. So Jackson gives you a very descriptive, big amount of description of what went wrong. Gson says, we read a string and it wasn't what we expected. Moshi gives you a path. So it says, I was reading the JSON and I wanted a long, but it was the string whoops at response.hits element 8 result.id. And then Kotlin serialization just tells you what went wrong. And so I think that these different libraries, ultimately, if you can go from the error to finding what you need to fix, that's good. I don't like how Kotlin serialization just crashes. If you give it a value that's a valid JSON number, but not the exact type, like if you say in code it's a long, but in the JSON it's 1.0, Kotlin crashes. I think this is probably a bug. It's something that they'll have to fix, but it's going to ultimately complicate their system. When a required field is absent, Jackson and Gson actually, in some cases, will just ignore that it's absent and replace it with a default value. So for example, if you have a required field in your Kotlin, something that doesn't have a default and is not nullable, Jackson will actually will just provide 0 there. The 0 sort of comes out from nowhere and shows up in your JSON model. Moshi will throw and say the required property ID is missing, and Kotlin serialization will do the same. If the document you parse is empty, Gson does something super weird. It just turns empty documents into null. This is a bug, but it's really hard to fix without breaking compatibility. If you try to write a platform type, earlier I was talking about writing color. If you try to write future, Jackson and Gson just do what you ask it to do, but I think that that's a bad design. Both Moshi and Kotlin serialization force you to say which types you expect to be converted to JSON, or at least won't encode platform types. If you give it a type that's of too big for an int when you're parsing, Jackson, Gson, and Moshi will all give you instructions as to exactly where the value is of the wrong type. But Kotlin serialization just crashes with an unhelpful exception. And then you have to go out and say what field was wrong. In this case, you never get the string annotation count, which is the one where the type was wrong, and that's where you have to fix something. So here we have the awards. We're going to present our awards to our favorite JSON libraries. Most capable is definitely Jackson. This library is huge. It can do everything you want. If there's something you can imagine, Jackson can do it. Gson is a very, very popular JSON library, and that's mostly what I have to say about it. Obviously, I'm incredibly biased. Moshi, I think, has the best API. We've really focused on usability and making it so that you spend most of your time thinking about your application model and not about JSON. And then, of course, Kotlin serialization is awesome. It has support for multi-platform, and it's the one to watch. So 2 more sections. I want to talk about testing. Basically, you should test your JSON. Basically, you should confirm that the JSON that you're reading and the JSON that you're writing work, and you want to get your server team to code review it. And it just looks like something like this. Like, include some JSON in test case, and then convert it from JSON to your value and convert it from your value to JSON, and just confirm that it works. And so if you accidentally do the type mapping wrong, or if you've got something misconfigured, you'll see it here. If you do some refactoring and you accidentally rename something, you've got a test that will crash. So we've got our JSON. We want to make it faster. There's a bunch of different ways. Easiest way is just to use less JSON. Don't use pretty printing. Take the white space out. Take the unused fields out. Omit nulls. The less that you have to encode and decode, the faster things will be. Avoid reflection. So enable generated code. And then if you're using something like Gson, you can get the adapter and then reuse that every single time. That just saves a bunch of allocations and lookups. And really, if you want to make your JSON faster, use streaming encoding. So download and decode in parallel rather than doing all of your downloading and all of your decoding. If you're doing streaming uploads, make sure your models are immutable. It's really problematic if while you're uploading a value and the user edits it, if the upload changes or it could potentially tear. And then this is like kind of probably the most controversial advice I have for today. I think that if you really care about performance, if like performance is something that's a problem to you, you should consider coupling your JSON with a technology like protobuf that uses a binary encoding. You can use protobuf as a schema language and just say we're going to define what our APIs look like with protobuf. Agree exactly what the fields look like for clients and servers, but still keep JSON encoding. You still read and write JSON even though protobuf is effectively the schema. But once you do that, then you get the option of using protobuf as a binary encoding. And so what I like about protobuf here is that it's if you really care about performance, if you're having performance problems, JSON may be the wrong tool for you, but you can progressively go from JSON to protobuf without rewriting your entire application. So that's the JSON explained. Thank you very much for listening, and good luck out there.